Imagine falling into a place where gravity becomes so powerful that even light cannot escape, a place where time itself begins to slow down and the laws of physics start to break. What would actually happen to you? Would you be crushed instantly? Would time stop? Or could you somehow pass through and discover an entirely different universe on the other side? Black holes are among the most mysterious objects in the cosmos. They swallow stars, bend space and time, and hide their secrets behind a boundary called the event horizon. But the biggest question scientists still ask is this: what really happens inside a black hole? Today on Simple Physics Lab, we're going on a journey to the very edge of the unknown and possibly beyond it. Black holes are often described as cosmic monsters. They devour gas clouds, destroy nearby stars, and sit at the centers of galaxies like enormous gravitational traps. But despite their terrifying reputation, black holes are not simply destructive forces. In fact, they are some of the most fascinating laboratories for understanding the deepest laws of nature. They challenge everything we think we know about space, time, gravity, and even reality itself. A black hole is created when an enormous amount of matter is squeezed into an incredibly tiny region of space. The gravity becomes so intense that nothing can escape. Not particles, not radiation, not even light. This makes black holes invisible. We cannot see them directly, but we can see their effects. We see stars orbiting something invisible. We detect powerful jets of energy shooting from their surroundings. And in 2019, humanity captured the first ever image of a black hole's shadow. Even today, black holes remain one of the greatest puzzles in modern physics, because once something crosses the boundary of a black hole, we lose all information about what happens next. Or at least, that's what we think. So today, we will explore what scientists believe happens inside a black hole, from the edge of the event horizon to the mysterious singularity at its core. And along the way, we may discover that black holes are not just cosmic traps. They might be the keys to understanding the universe itself. The story of black holes actually began long before space telescopes or modern astrophysics. It started in the 18th century. In 1783, an English scientist named John Michell had a strange idea. He wondered, what if a star were so massive and its gravity so strong that even light could not escape? At that time, people believed light behaved like tiny particles. If gravity could pull on objects, then perhaps it could pull on light too. Michell calculated that if a star were dense enough, its escape velocity would exceed the speed of light. That star would become completely invisible. He called these objects dark stars. But the idea was largely forgotten. Then, more than a century later, something revolutionary happened. In 1915, Albert Einstein introduced the world to general relativity, a theory that completely changed our understanding of gravity. According to Einstein, gravity is not simply a force pulling objects together. Instead, massive objects bend the fabric of space and time itself. Imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet curves downward, and smaller balls roll toward it. That curvature is what we experience as gravity. Soon after Einstein published his theory, a German physicist named Karl Schwarzschild found a mathematical solution describing what would happen if an enormous mass collapsed into an extremely small point. His equations predicted something remarkable, a region where space-time becomes so curved that nothing can escape, not even light. This was the first theoretical description of a black hole. But for decades, many scientists thought these objects were just strange mathematical curiosities. Surely, nature wouldn't create something so extreme. Then in the 1960s and 70s, astronomers began discovering incredibly powerful objects in distant galaxies, sources of energy so bright they could outshine billions of stars. The explanation? Supermassive black holes. Today, scientists believe nearly every large galaxy, including our own Milky Way, contains a giant black hole at its center. And suddenly the question was no longer, do black holes exist? The real question became, what is happening inside them? To understand what happens inside a black hole, we must first imagine approaching one. Picture yourself in a spaceship drifting toward a black hole floating in deep space. At first, nothing seems unusual. From far away, a black hole behaves like any other massive object. If the sun were replaced by a black hole with the same mass, Earth would continue orbiting exactly the same way. But as you move closer, strange things begin to happen. Light from distant stars bends around the black hole. The sky behind it appears warped and distorted. This effect is called gravitational lensing. The black hole is bending space itself, forcing light to follow curved paths. As you continue moving inward, gravity becomes stronger and stronger. Then you reach a very special boundary, the event horizon. The event horizon is often described as the point of no return. Once anything crosses this invisible boundary, escape becomes impossible. Not because something is pulling you back, but because every possible path through space-time now leads deeper into the black hole. Even if you fired rockets at full power, even if you moved at the speed of light, you could never come back out. But here's something surprising. If you cross the event horizon of a very large black hole, you might not notice anything special at that exact moment. No sudden wall, no flash of light. From your perspective, you would simply continue falling inward. However, something very strange would be happening to time. According to general relativity, gravity affects not only space, but also time. The stronger the gravity, the slower time moves. This phenomenon is called gravitational time dilation. Near a black hole, this effect becomes extreme. To an outside observer watching your spaceship, something bizarre would happen. As you approach the event horizon, your motion would appear to slow down. Slower and slower and slower. Eventually, you would seem to freeze in place. Your clock would appear to stop, and the light from your spaceship would slowly fade away. From their perspective, you would never actually cross the event horizon. You would remain frozen there forever. But from your own perspective inside the spaceship, time would feel perfectly normal. You would pass through the event horizon without noticing anything dramatic. This strange disagreement between observers is one of the many mysteries of black holes. It shows that time itself is not absolute. It depends on gravity and motion. And near a black hole, time behaves in ways that seem almost impossible. As you fall deeper into the black hole, gravity continues to increase dramatically. But the real danger comes from something called tidal forces. Gravity becomes stronger the closer you get to the center. That means the force pulling on your feet becomes stronger than the force pulling on your head. This difference stretches objects apart. For a human falling into a smaller black hole, the effect would be catastrophic. Your body would be stretched into a long, thin shape. Scientists call this process spaghettification. Your atoms would be pulled apart one by one, forming a stream of matter spiraling toward the center. However, if the black hole were extremely massive, like the supermassive one at the center of our galaxy, the tidal forces at the event horizon might actually be relatively gentle. You could cross the event horizon intact, at least for a while, but eventually, as you fall deeper, the stretching would become unavoidable, and all matter would ultimately be pulled toward a mysterious point called the singularity. At the very center of a black hole lies the singularity. This is a place where density becomes infinite, and space-time curvature becomes infinite. In simple terms, all the mass of the black hole is compressed into an infinitely small point. Our current laws of physics completely break down here. General relativity predicts the singularity, but it cannot describe what happens inside it. The equations stop working. Some physicists believe that a future theory called quantum gravity will eventually explain what really happens at the singularity. Until then, it remains one of the greatest mysteries in science. Is the singularity truly a point of infinite density, or is it something else entirely? We simply don't know. Black holes are filled with astonishing surprises. For example, black holes are not entirely black. In the 1970s, physicist Stephen Hawking discovered that black holes can slowly emit radiation. This phenomenon is called Hawking radiation. It occurs because of quantum effects near the event horizon. Over incredibly long timescales, this radiation causes black holes to lose energy and slowly evaporate. A black hole the size of a star would take longer than the age of the universe to disappear, but eventually even black holes may fade away. Another surprising fact is that black holes can grow to enormous sizes. At the center of the Milky Way lies a supermassive black hole called Sagittarius A*. It contains the mass of about 4 million suns. Some black holes in other galaxies are even larger, containing billions of solar masses. These cosmic giants influence the formation and evolution of entire galaxies. Black holes also create some of the most powerful explosions in the universe. When matter falls into a black hole, it forms a swirling disk called an accretion disk. The gas heats up to millions of degrees and releases tremendous energy. Sometimes, black holes launch enormous jets of particles traveling near the speed of light. These jets can extend for thousands of light years across space. Black holes may seem distant and irrelevant to our daily lives, but studying them has helped scientists understand fundamental physics. For example, the study of black holes led to breakthroughs in our understanding of gravity, quantum mechanics, and information. One famous puzzle is called the black hole information paradox. If black holes eventually evaporate, what happens to the information contained in everything they swallowed? According to quantum physics, information cannot be destroyed. But if black holes erase information, that would violate one of the core laws of physics. Solving this paradox could lead to a deeper theory uniting gravity and quantum mechanics. In other words, black holes might help scientists discover a theory of everything, a single framework explaining all forces of nature. Black holes also help scientists detect gravitational waves. In 2015, detectors observed ripples in space-time produced by two merging black holes. This discovery opened an entirely new way of studying the universe. Instead of observing light, we can now listen to the vibrations of space itself. Even today, black holes continue to surprise us. Astronomers are building more powerful telescopes to study them in greater detail. The Event Horizon Telescope network may soon produce even clearer images of black holes. Scientists are also studying the possibility that black holes could contain wormholes, tunnels connecting distant parts of the universe. If wormholes exist, they might allow shortcuts through space-time. However, this idea remains highly speculative. Another fascinating idea is that black holes might create new universes. Some theoretical models suggest that the singularity inside a black hole could lead to the birth of another expanding cosmos. If this is true, our own universe might have originated inside a black hole from a previous universe. While these ideas remain unproven, they show how black holes push the boundaries of imagination and physics. Black holes are more than just cosmic vacuum cleaners. They are windows into the deepest mysteries of the universe. They challenge our understanding of space, time, and reality itself. When we ask what happens inside a black hole, we are really asking something much bigger. We are asking where the laws of physics end and where new ones begin. Perhaps someday humanity will develop a theory that fully explains black holes. Perhaps we will discover what lies beyond the event horizon. Or perhaps black holes will always remain partly mysterious, reminding us that the universe is far stranger than we ever imagined. But one thing is certain. Every time we study black holes, we learn something profound about the cosmos and about our place within it. If you enjoyed this journey into the mysteries of black holes, make sure to subscribe to Simple Physics Lab. We explore the most fascinating questions about space, physics, and the universe using simple explanations anyone can understand, because the universe is full of mysteries, and together we can explore them. Until next time, keep asking questions